So now we look into this problem, all pair shortest path problem. So all pair shortest path. In the last lecture I already told you what do we mean by this problem. So given a graph G and any pair of vertices, we are required to find out the shortest path between those two vertices. So in this case I am going to give you one algorithm which is based on matrix multiplication. There are two algorithms for this problem we will study, and the first algorithm I am going to give you now, it is based on some matrix multiplication. So I am assuming this time the representation of the graph is by a matrix. So let us take an input graph, say this is the graph. Two point three, 4.5, 3.2, and say this is another one. I am just taking a directed graph in this time. It works also for undirected graph, it does not matter. So the adjacency matrix for this graph will look like something like this: 2, 3, 4. No, that I will direct soon. So 1, 2, 3, 4. So all the diagonals this time will put 0. So between 1 and 2, this is 2.2, 1 and 3. So this time I will put this way: 1 and 3, this is 3.2, and 1 and 4, 2.3, and these are infinity, infinity, infinity. Basically there is no edge. Infinity, infinity. This is 4.5, infinity, infinity, infinity. So this is the adjacency matrix representation of this particular graph. Now so what we want to do, given this adjacency matrix, say some D, we want to output another matrix, say matrix D prime, where we should have this: Dij, D prime ij is actually equal to weight of the shortest path from I to j. So this is what we want. So how do we do this? So we'll keep this one in mind, later we may come back. So shortest path, so let Dij, this is my definition, Dij superscript m, m is the number of edges in the graph, remember. So Dij superscript m is equal to the weight of the shortest path from I to j that contains, this is just a definition, at most m edges. So this is important. So suppose Dij superscript m denotes the weight of the shortest path from I to j which contains at most m edges. Among all such paths which contains at most m edges from I to j, Dij superscript m will give you the shortest path among all such paths. Now can we write a recursive definition of Dij m? If we can write a recursive definition of Dij m, we will see that will give us some algorithm. So let us see Dij first, this is easy, Dij 0, that means path from I to j without any edge, 0 number of edge. This is what? Is equal to 0 if I equal to j, otherwise infinity, otherwise if I not equal to j. So this is the basically base case definition, because we are going to give a recursive definition. Now comes the interesting part. Dij superscript m, I can write that one as minimum over this. Either it is Dij m minus 1 or it is another minimum over all k between 1 to n. I will explain this one. Dik m minus 1 plus wkj. And this is the most crucial definition here, or crucial relation. Once you understand this, you will understand the algorithm almost immediately. Okay, why are we getting this? Let me just explain this one using the picture. So what is Dij m? So you take I, the vertex I here, you take the vertex j here. So suppose there is a path, this is the shortest path actually from I to j, which is using less than equal to m edges. So this is less than equal to m edge it is using. Actual Dij m, this is the weight of this path is Dij m. Now look at the last stage here. So there is a last stage before reaching j. Now this vertex is the vertex k. Now this k can be anything between 1 to n, it cannot be anything else because all the vertices are indexed between 1 to n. So this last vertex k must be one of the vertices from 1 to n. So what you do, you take the weight from I to j going through all k then to j, and this must be the least among all of them. So what is this part then? What is the weight of this part? It is nothing but Dik using at most m minus 1 edges. So this is Dik m minus 1 plus weight of kj. So if you take, so this is less than equal to m minus 1 up to k. So if you take Dik m minus 1 plus this is wkj. So this is this. Now you vary k from 1 to n. For one value of k, you will find actually this path. So that's why if you go back to the definition of Dij m, this is your second part. You take the minimum over all such k. And what is the first part? First part is maybe that does not, you don't need to go through this at most m edges at all. This is assuming that you need to go through at most m edges. Maybe the previous Dij m minus 1 is already there, is better than all this. So you take the minimum of this one and this one, which definitely has to be equal to Dij m. Your Dij m is either equal to Dij m minus 1 or minimum of this. Actually we will see in the algorithm we can include this one here also. How? I can delete this part totally. When k is equal to j, just look at it. When k is equal to j, this is minimum of Dij plus wjj. What is wjj? 0. So that will automatically take care of this Dij minus 1. Actually I don't have to write it explicitly. This is enough. And that's what we will, so once you have understood this, we can go over the algorithm. So let me now write down the algorithm, then I will explain again how the algorithm proceeds. So I am assuming that we are inputting one matrix and we are creating a new matrix. So the input matrix is this. So this is called extend shortest paths DMW. So the input matrix is D superscript M and output matrix will be D M plus 1 superscript M plus 1. There are two matrices. So let D M plus 1 is equal to Dij basically M plus 1 be an n cross n matrix. I am going to write now for I is equal to 1 to n, for j is equal to 1 to n, you initialize dij m plus 1 as infinity. This is just an initialization of this matrix dm, the output matrix. I am just initializing it. Now here is the another for loop where k is varying, k is equal to 1 to n. Now I am going to implement that recurrence relation. K is varying from 1 to n. So what dij m plus 1 must be equal to minimum of what? Minimum of dij m plus 1 comma, this is fine, this is not m, this must be this is the algorithm, because you have to update this value again and again. Remember what this for loop will do, how will you keep the minimum? So you have already assigned for some value of k, you have assigned dij m plus 1, that has to be updated, so that has to be taken here. So that change you need to make. So that's why minimum dij m plus 1. Then here what you are saying, dikm plus wkj. This is the second part. This I just put because you need to update your dij. This is a variable. This is one variable. So for say k is equal to 1, this has got one value. So how will you get the new one? So new one will get minimum of the between these two, right? When k is equal to 2, you will calculate this. How you will get the minimum between k is equal to 1 and k is equal to 2? You will take the minimum of this and this. That's why you have put this. So this is n4, n4 and n4, and you return d m plus 1. So this algorithm, what it is doing, it has got all the shortest paths which are using at most m edges, then it is putting those values which are using at most m plus 1 edges. It's just going from m to m plus 1 edges. So this is the calculation, because that is the recursive definition, already we have seen. So this recursive definition is captured exactly here. Only somebody was objecting on this, but I already told you why you need to put this one. If you don't put, just see, if you don't put this, what will be happening? Dij is equal to m plus 1 is equal to dik m plus wkj. But then every time for new value of k, you will be putting that the last value of k will be put in dij m plus 1. But you need to see what is the previous value and what is the new value. You should retain the minimum. That's why you need to do this. Take the minimum of the two. Okay, so how much time does this take? This is order of n cube time, because this is nothing but there are 3 for loops. Okay, can you, but have you seen the similarity between the matrix multiplication and this operation? What is the matrix multiplication? Matrix multiplication has this form. Matrix multiplication has this, suppose you are multiplying the matrix A and B, creating C, then how do you create? Cij is equal to sigma k is equal to 1 to n aik times bkj. That's the way you get one entry of a matrix. When you multiply two matrices, one entry of the output matrix. But look, suppose we replace this dot by plus and replace this sum by operation mean. What is it? It is exactly what we are trying to compute. Look at what we have done. We have aik means dik plus dkj, dik wkj, that is this plus, and here there is a plus operation. So there is a plus operation here, and this summation you are taking the minimum of all such sums, that is the minimum here. So if you replace the sum by mean and dot by plus, you will get exactly what we are trying to do. So this, what we have just done is nothing but you take the weight matrix W and suppose you multiply W with these changes of operation, you will get D2. You take the weight matrix, the adjacency matrix, multiply the adjacency matrix by itself with this change, plus dot goes to plus, plus goes to mean. In that case, W dot W, that is W2, is exactly equal to D2. You have got all the weights of the paths which uses at most 2 edges. Then again you multiply D2 with say another matrix W. What you would get exactly is D3. Again you multiply with another W, you will get D4. So if I write all, so this is our final algorithm, all shortest paths. The final algorithm is initially D1 is equal to the weight matrix W. W is the adjacency weight matrix, so that is W. Then from for M is equal to 2 to how many edges can a path have at most? Shortest path in a graph of n vertices, n minus 1. So your variable M cannot go beyond n minus 1. What will happen after you have multiplied n minus 1 times? If you go on multiplying again, it will remain the same. The matrix will stabilize. It will not give you any new value, because the weight of the shortest path using at most n minus 1 edges is same as at most n edges, at most n plus 1 edges. So we need to go from M is equal to 2 to n minus 1, and your dm is exactly equal to, you call that previous algorithm extend shortest paths with argument dm minus 1 and multiplied with W. Take this 2 and then you will get this. Remember in that algorithm we had 2 parameters, so we supply this parameter, and that is n4, and return ultimately dn minus 1. And what I just said is dn minus 1 is same as dn, same as dn plus 1, it goes on, it does not change. After n minus 1, if you go on multiplying W with dn minus 1, you will get a matrix which is same. So we need to go only up to n minus 1, that is what it is. Yes.
Initialization says Dij n plus 1. I think it should be initialized to the previous value at the end. You initialize to infinity.
Now this is fine. So his question is, he is asking in the extend shortest path algorithm, Dij m plus 1 should not be initialized to infinity. It should be initialized to what according to you?
The previous value in dm.
No, dm is already, yes, we could have done that one also. What you are saying, if I initialize Dij m plus 1 is equal to Dij m, that is also fine. Anyway, that will be encountered in mean, but this is also okay. What you are suggesting is also right. I could have also written that Dij m, because anyway Dij m plus 1 will go over that value, so I can as well put that value here, okay, but putting infinity is also alright, both are okay. Now how much time this algorithm takes? This is your shortest path algorithm now, it gives you weights of all the shortest paths. So how much time does this take? Order n to the power 4, because one extend shortest path takes n cube and you are doing it n times. So this will be order n to the power 4 algorithm. So this is an n to the power 4 algorithm. So matrix multiplication using this method, we get a order n to the power 4 algorithm. All right. Yes, there are some objection, or maybe somebody has already observed that we already said it should be n cube log n, y into the power 4 then. But we can easily improve that algorithm by doing this simple trick. What is that trick? You compute this, d1 is equal to w, we know, then d2 is equal to w square, w cross w. Now going to d3, I would not compute d3, I will straight compute d4, because I know w square I have computed. If I multiply with w square, I will get d to the power 4. So next one, I will not compute 5, 6, 7, I will compute 8. So it will be w to the power 4, w to the power 4. So if I go on doing this, ultimately d to the power 2 to the power log is a seal. Log n minus 1, if we do this many times, what we will get? We will get basically d to the power n minus 1. So you see, now we are jumping. You first take 1 1, then 2 2, then 4 4, then 8 8. So to reach n, how many times you will have to do? Something like log n time. So if you multiply, so how can you write this? So d to the power 2 to the power log n minus 1 is equal to now w to the power 2 to the power log n minus 1 still. This you can write w 2 to the power log n minus 1 minus 1, again multiply with the same thing, 2 to the power log n minus 1 minus 1. Okay, so this is what you do. So how many steps? Then if you do this multiplication in a binary fashion, then what you will get? This loop you don't have to do n times, you will have to do it log n times. So each time you have n cube and you are multiplying totally log n times. So total algorithm complexity becomes n cube log n. So this will give you, this entire procedure will give you order n cube log n. So now we can compute all pair shortest paths using the time n cube log n. And if you have already observed, in this case we did not talk about any negative weight or positive weight. No matter what are the weights are, this algorithm works. Now, let me point out in Dijkstra's algorithm why negative weights create a problem. Now, Dijkstra's algorithm assumes whatever path you have taken through the S, if you take one more edge, the weights increases, or path weights of the path increases. But when the weights are negative, this is not true anymore. Even you can decrease the weight of a path including more edges, and that's why Dijkstra does not work. But here we did not say anything about negative or positive. We basically is something like a very exhaustive searching. We looked into all possible ways of k and took the minimum. So that's why this works. So this is one way of doing all pair shortest path. In our next lecture, what I will take up, the next algorithm for all pair shortest path, which is called the Floyd-Warshall's algorithm. So there we will see this entire time complexity can go down from n cube log n to only n cube. In this case, actually even if it is n cube log n, there are many matrix multiplication. Log n times you will be multiplying two matrices, but in that algorithm we will multiply only one matrix, only once two matrices actually, and you will get the solution. And actually the algorithm is very simple. It is again the only 3 for loops, but only we have to look at the problem or this recurrence relation a little bit differently. We will set up again the same type of recurrence relation for the shortest path weights, but we will have to look at this value k differently. So if we do that, we will get a better algorithm. That we take up in the next class.